mass of the planet divided by the I squared. If I'm looking for the point at which it will never escape, no matter how fast, it will never escape, I'm basically going to put my maximum speed in right here. So this becomes 2gmx over the speed of light squared. So c is the speed of light. So let's just start with the Earth. If I take the Earth, it's going to somehow magically, without getting rid of any mass, shrink the Earth down. How small would the Earth be so that the speed of light is not enough to be the escape speed? So all I'm going to do is I'm going to plug in the mass of the Earth, everything else is a constant, to figure out what the radius of the Earth needs to be to become a black hole. So this is 2 times 6.67 times 10 to the negative 11th times the mass of the Earth, which we have all know and love, 5.98 times 10 to the 24th, divided by the speed of light, which is roughly 3 times 10 to the 8th. And then we'll square that denominator. So if we're going at the maximum speed, this is basically the radius of the Earth. So we're finding the radius so that you need to go to the speed of light in order to escape. It's the cutoff. So someone is going to reveal what this value is. That is 8 there.
Point 00886.
0.00886.
86.
886 or just 86?
2 eighths.
Okay. Units?
Meters?
Yep, the radius. All right, so that's almost 9 millimeters. That's the radius. So the Earth could somehow magically take all the mass that's on the Earth right now and get shrunk down so that the diameter is basically between my 2 fingers. The Earth would become a black hole. Because because you are so close to the center of the Earth that you would have to go to the speed of light even with any hope of being able to escape, but we could never go to the speed of light because we are starting out slower. Now, our Earth cannot be compacted that much, to our knowledge. So let's take a star, because black holes generally come from stars. Let's take our star. We're going to do the same plug and chug, except this time we'll plug in the mass of the sun. So how big does the sun need to be? And mass of the sun, 1.99 times 10 to the 30th kilograms. So for our sun to become a black hole, the radius of the sun would need to be 2 times 6.67 times 10 to the negative 11th times 1.99 times 10 to the 30th divided by 3 times 10 to the 8th squared. Lydia, you look like you're trying to read something.
I don't know, I was just trying to see where
Lacey, what do you have?
2,949.62.
2,949.
Yes. And then
Point.
0.6 with a lot of twos after, so.
Two
6
repeating.
Yeah. Or, no, 6, 2 repeating. Like the two's repeating after the
6, 2
six.
repeating.
Oh, 6, 2 repeating, okay.
Yeah.
Units?
Meters.
Yeah.
All right, so a little under 3,000 kilometers. Sorry, try that one again. A little under 3,000 meters, a little under 3 kilometers. So if we double that for the diameter, so a little under 6 kilometers, is that Peters Creek to Haynes Mall? If our sun shrank down to that size, our sun would become a black hole. Because again, in order to escape it, the escape speed is the speed of light, and anything that starts out slower than the speed of light can never get there. So let's talk a little bit about our sun and the black hole. Questions before I talk about current theory? So when you have stars, you got two major processes going. In the star itself, you have hydrogen atoms, which are basically combining to create helium, and when they do that, they give off energy. This is the essence of the hydrogen bomb. Because, as I've said, potentially not to you, but I think so, all physics leads to weapons. So I take these two hydrogen atoms, I combine them, it creates helium atom, and then gives off energy. That energy is being radiated outward in the sun. So if we take our sun, I have radiation trying to get out. This is known as creating radiation pressure. At the same time, I have all this mass inside there, and it's trying to be pulled together. So I have radiation trying to come out, but I have gravitational forces trying to pull it in. And the stars have these two major factors playing on them. And when one wins out, it either gets bigger or smaller. So because every time it loses energy, it loses a little bit of mass. And so it's losing mass as it goes. And when all the hydrogen is used up, then the heliums will combine to create whatever 4 on the periodic, oh, we have one right here, to create beryllium. And a little less energy. When you have two heliums get together to create beryllium, they don't give off as much energy as two hydrogens. That's why there's not a helium bomb, there's a hydrogen bomb. When all the helium's used up, it just works its way down until we get to, I think, iron. Iron is basically at that point, I'll double check that. At some point, you get no energy by two atoms coming together. Now, above whatever that is, then you get energy by splitting it. So, thus, the atomic bomb, you get energy out of it by splitting the atom. But our sun is more of a hydrogen bomb. Now, if you lose enough mass through this energy, because this whole mass, when I talk about rest energy, the fact that we can have mass and energy are almost used interchangeably at some point. As the energy goes out, it loses mass. If the mass drops off enough, we will no longer have this pull coming in, and so the star will start to get bigger. And that basically is what is expected of our sun. Some people say, at what point will the Earth be swallowed up by its sun? Actually, it won't be. As the sun is losing mass and starts to expand, the gravitational pull on Earth will become less, and so Earth is actually going to move farther away. At some point, the sun will be here, but the Earth will not be. And humans won't be around by then, at least not on Earth. Now, if there's a lot of mass there, when it burns through all the hydrogen, there's still so much mass there that it's basically, you lose the radiation pressure, and it's going to come collapsing in on itself. If it collapses in, some stars will then they collapse in so quickly that they will compress, a lot of heat is generated, and it will explode. Then we have a nova or a supernova. If it's even more massive, it will collapse in. The gravitational pull is such that it will not be blown apart because the gravitational pull is so strong, and we get a black hole, assuming it collapses into a small enough radius. When Einstein came up with his theory of general relativity and the math behind it in 1915, how you get there changes, but the formulas still actually work. The guy who basically went through this is a guy named Schwarzschild. I don't think there's a T in there, but I think that's spelled right. He was a German physicist who got drafted. He eventually got inhaled at the wrong time during a mustard gas attack and ended up in the hospital while he was recovering. He worked on general relativity. The radius, the formula we have for the radius, he used more sophisticated math in order to get to the same place, but this is known as the Schwarzschild radius. So we're covering actually two major papers. This was probably the one that's more famous. And he eventually dies from his injuries. There are a number of very notable physicists who died during World War I. So anyway, the Schwarzschild radius. And I think at that point, only thing we haven't officially talked about is projectile motion, but I'm sure you can figure it out from the videos and the textbook. So the big thing on number 8 is that when you watch something horizontally, the time it takes for an object to fall is the same time it takes for it to hit the ground going out. I'm pretty sure we did a demonstration with that years ago, somewhere near the beginning of the semester.
Can you say that again?
When you shoot a ball horizontally, it will be in the air the same amount of time as something that just falls straight down. So if I want to know how long something is going to be in the air, I take an object from rest, I drop it, how long does it take? But on that note, the note that we will never actually be swallowed by the sun, there's one beat note right there. I hope you have a wonderful weekend.
Thank you.